Hello everyone, welcome to today's video on developing empirical models. Today you explore how to build empirical models for process, mixture, and mixture process designs. Models in experimental design, particularly empirical models, they play a very central role in helping you understand how the input factors and the response variables uh, they relate with each other. And in optimizing your responses, models are always very paramount in helping you predict the optimal conditions, since most of the times the base experimental runs will not result in the optimal condition. So models are always very important as it will help us go closer to the optimal condition as fast as possible. Let's look at models for process designs. Consider a process which involves the drying of a food product. They have given you some factors that affect the drying rate. The first factor is the air velocity. The second is the temperature. The third is the food thickness. And the fourth is the relative humidity. So you've been asked to develop a model that will relate all these factors together, how these factors work together to reduce the moisture content. So here the response is the moisture content of the food product. So to develop a model, you have to start with the intercept. It gives us the starting point of your model. So the next step is to go further to develop how all the factors they affect the drying rate. And here you look at the single effect of the factors in a linear model. Then after looking at the single effects, you go to the interaction terms, how these factors they interact with each other to affect the moisture content. If these factors work uh, efficiently when you treat them independently, or what is the interaction effect on the response, in this case, the moisture content. So the third step is to develop a quadratic terms. The quadratic terms actually gives us an idea where the best combination of the factors to reduce the moisture content is. For example, let's say this is an expanded linear form of the model where you have the beta zero, which is the intercept, and then the linear independent terms, which is the effect of velocity, the effect of temperature, the effect of the food thickness, and then the effect of relative humidity. The linear terms tell us which factor contributes to the response more than which factor. So in this case, if you are having more than four factors, you would treat the four factors independently using the linear model so that you can identify which of the factors significantly affects the response so that in the course of developing the quadratic model, you can select those factors that significantly affect the response and then you continue from there. Look at this scenario where the starting point is 22. This means that if you don't vary the, the independent variables, the moisture content of your food product will be 22. If you set x1, x2, x3, and x4 at 0, it means that the moisture content of your sample, which is actually the intercept, could be at 22%. And when you start varying the factors, the moisture content will also start changing. So if you set the value of x here at 0, you have a value of y, which is actually beta 0. With this simple model, you can see that x1, x2, x3, x4 to affect the moisture content differently, the drying rate differently. Looking at the regression constant of x2, you can see that temperature actually affects the drying rate, followed by the air velocity, followed by the relative humidity, and lastly by the food thickness. This is just a representation to show you how the linear terms and regression constants can be used to decide which factor affects a response more than which factor. Let's look at the expanded form of a quadratic model involving three factors. We are considering that from our linear model, three of the factors were significantly affecting the drying rate more than one of the factors, which is air velocity, temperature, and relative humidity. And the response is the moisture content. So to develop a quadratic model for the three terms, we are looking at the intercept plus the three effect of the single factors as they affect the drying rate, the combination between the two factors, that is the interaction terms x1, x2, x3, x1, x2, x3, and then x1, 2, 3. And then the quadratic term is the interaction between each factor and itself. When you develop this type of models, you see that you have 1, 2, 3, 4, 11 constants. To actually evaluate for these constants, you need to develop an experimental design that has at least 11 runs before you can evaluate for these constants and actually optimize the process. Before we look at the models for mixture designs or the Sheffield models, remember this fundamental constraint for mixture experiments, where summation x of I is always equal to 1. This means that the sum of all component proportions in a mixture design is always equal to 1. So with that said, let's present the general form of a mixture design model. The first term here represents the linear model terms, which is just the effect of the single ingredients on the response. The next term is the quadratic term, which is the double effects, the double interaction effects of the ingredients, how the ingredients interact with each other to affect the response. The third term is the special cubic term, while the fourth term is the real cubic terms. So here, notice the difference between a mixture model and a process model. The first difference is the absence of beta zero. There is no beta zero in the mixture model. Why? Because the intercept, which is actually beta zero, is a point on the y-axis where the values of x, they are 0. This is x and this is y. Then the beta 0 is the point on this axis where the value of x is 0. Because in a mixture model, because in a mixture design, the values of x are never 0, there is the absence of this beta term. The general form of a mixture model is sounding a bit complex, but let's break it down here. If we consider this y to be the quality parameter of a food product, let's call it protein content per se. So what is the effect of x1 on a protein content? Remember that x1, x2, x3, they are the ingredients in the food product. x1, x2, and x3, they are the ingredients used to formulate the food product. So what is the effect of ingredient x1 on the protein content? What is the effect of x2 and x3? The effect of these single components gives the linear part of the model. This is a linear model. And the beta terms gives the magnitude of the effect of these single terms. If beta 1 here was equal to 3, beta 2 equals to 5, and beta 3 equals to, let's say, 1. This means that ingredient x2 has a beta effect on the protein content. Ingredient x2 increases the protein content of the food product more than ingredient x1 and more than ingredient x3. So looking at the single effects, okay, let's go further. If you combine these three components together, are there some ingredients, or will a combination, or is there a way these ingredients will have an interaction effect on the protein content? How will these ingredients work together? Will they work together to improve or reduce the protein content of the food product? This is when the quadratic terms will come in. And here, also notice the difference between the quadratic term. Is the quadratic term. Also notice the difference between the quadratic term of a process model and that of a mixture model. In the process model, x2 is raised to the power 2, whereas in a quadratic model for mixture designs, it's just the double interaction between the component proportions. And the special cubic term is actually the interaction between all the components. And of course, E is the experimental error. So for you to develop this experimental design, for you to develop this experimental setup and evaluate the effects of all these components on the response variable, you need 1, 2, 3, 4, 5, 6, 7 experiments. So the model already tells you the kind of design you should use. The model already tells you how many runs or how many experiments or how many samples you need to evaluate and get the optimal formulation, or evaluate and get the optimal effect of component proportions on the response variables. Now let's look at something more interesting: models for mixture process designs. This structure allows you to explore the interactions, or explore how mixture components they interact with processing conditions, how formulations can interact with processing conditions to affect the response variables. And this is very ideal for food, pharmaceutical, chemical, and any experiment that deals with formulation. The issue is that in process industries, the quality of any output is always dependent on the simultaneous function of the mixture variables or the ingredients used in formulating that output and the processing conditions used to process that output. So with that, it's always difficult to study just the processing conditions or study just the mixture ingredients. And mixture process designs, they are out there to help solve the complex interactions that always occur between these process and mixture variables. The general form of a mixture process design is presented as such, and it's looking complex when you look at it at a glance, but it's not actually complex. If you look at these first three terms, this is actually similar to the model for a mixture design, where you talk of the linear terms, the quadratic term, and a special cubic term. Now, looking at the model for this mixture design, you can see how the mixture variables, they affect the quality parameter. It's not just the mixture variables that affect the quality parameter. For example, if you were looking at the baking process, you are baking a product where the ingredients used in formulating the product and the baking time and temperature, they also affect the quality of the product. You may want to also evaluate how these conditions, like temperature, how temperature affect the quality of the baked product, uh, and how temperature and time affects the quality of the baked product in combination. So looking at the second series of terms, it tells you the effect of how formulation and the single effect of the processing conditions, they affect the quality of the overall product. You can see from here that this L, this Z of L, where L starts from 1 to R. If you had R equals to 2 for two different processing conditions, let's say temperature and time, it means you are going to multiply this first term, first of all, with temperature, which is Z1, and you also multiply this term again with time, which is equals to Z2, if R is equals to 2. The third term is actually the multiplication between the double interaction between the processing condition, that is temperature and time. How does temperature and time interact with the processed ingredients to affect the overall quality of the baked product? You can see here that this is also similar to the model for a mixture design multiplied by the combined effect of the processing conditions. Let us break down the complex form of a mixture process design using a very simple example. Let's consider a process again that involves the baking of a product, and we are combining two ingredients, X1 and X2, and we want to know how the combination of these ingredients affect the protein content. And again, we want to know how the processing conditions, like we are baking, how the processing temperature and the duration of baking, the processing time, affects the protein content. So in this case, we are first going to develop the mixture design model for the process, which is actually the effect of ingredient 1 and ingredient 2 on the protein content, and then the interaction between the two ingredients on the protein content. To go further developing the interaction between the processing variables, you have to multiply this set of terms. You have to multiply this set of terms with the first processing condition. If you see the first processing condition, Z1 is the temperature, and the second one, Z2, is the time, then we have to multiply this set of terms with temperature. If we do that, then we form this series of terms. You can see that this series of terms are multiplied by Z1. Again, to know the effect of time and formulation on the protein content, we have to multiply this series of terms again with the effect of time. If we do that, then we have this series of terms. And as you can see, they are multiplied by Z2. Now, the process design also has the interaction term between the process variables, which is temperature and time. How does temperature and time work together to affect the baking process? Does it affect it negatively or affects it positively? So with that, if we multiply this equation again with the double interaction between temperature and time, we are going to have this series of terms. And to know how many experiments you need to evaluate these complex interactions and study the simultaneous function of mixture variables and processing conditions on the quality index, you have to count the number of beta terms or the regression constants. And here, if you count from beta 1 to beta 1, 2, raised to the power 1, 2, these are just constants. The 1, 2 has no meaning. The 1, 2 has no uh, different interpretation. They are just constants. It can be gamma, it can be beta, or anything. So if you count these constants from beta 1 to beta 1, 2 to the power 1, 2, then you are going to have 12 constants. To evaluate for 12 constants in any equation, you also need at least 12 experiments to evaluate these complex interactions between the mixture variables and the processing conditions. Just as a recap, process models, they use polynomials like the first order and second order polynomials. Then mixture designs, they use the Schaefer models involving interaction terms, while the mixture process designs, they integrate these mixture designs and then the process design models to form complex models that will give out the beauty of any process that is involved with formulations.